So this goes back to a following problem which was posed and solved by Otto Radon in 1917. And the setup is this. You have a function on a plane and this function, depending on the formulation, is either compactly supported, that it vanishes outside some closed set, or alternatively it has sufficiently good decay conditions so that all the integrals I'm just about to write down are well defined. So compactly supported. Or so fast decay. Okay. Now what you want to do is construct another function out of f on the space of oriented lines on the plane. Okay, so this is a plane, and well, let's say that we work in the setup that the function is supported on some set. So there is some set on the plane where this function is non-zero. So it's here compactly supported on S. That's S. And now you draw all possible oriented lines. Here's a line. Here's another line. And to each such line, you associate the integral of this function along this line. So phi of L is an integral along L of f. Okay. Now, if you wanted to do it concretely, well, the whole point of this Radon transform and what he then did is that the space of line in R2 is also two-dimensional, and there are various ways of seeing it. I'll always settle for the most explicit one, even if it loses some generality, but we can represent a line by saying that if x and y are coordinates in R2, then a line will be given by S goes to, let's say, S, and then alpha S plus beta. So by choosing this parametrization, I'm assuming that the x coordinate is not constant on the line, so I'm losing some, like, codimension one worth of lines, but what the hell? So if I do that, then this integral becomes explicit, and I could say that phi of alpha and beta is just an integral over a real line from minus infinity to plus infinity of f, which now depends on s, and alpha s plus beta ds. Okay. Now, the result of Radon was that this transform can be inverted. So if I give you phi of L, and if I do so for all lines, then you can recover f. Radon says there exists an inversion formula. Which I'm not going to write down the formula for. Now, this inversion of formula of Radon was rediscovered in the 60s by somebody called Cormack. He was a part 3 student at Cambridge and then moved on to be a medical assistant in the University of, in Cape Town. And like a mathematician, really mathematician. And the rediscovery of radon transform earned him a Nobel Prize. So Cormack, I first give a year, so now I say 1979, Cormack gets a Nobel Prize in medicine. For rediscovering radon transfer, radon inversion, really. So to my mind, this is the closest it's ever been for a Nobel Prize be awarded for essentially pure mathematics. Well, why would that be relevant in medicine? You see, this is how, well, this is a setup for the X-ray transform. So in applications, you imagine some compact object which you want to build an image of, and then you're hit it with X-rays, and you can measure the intensity of the incoming ray. So you can measure some intensity here and the outgoing ray. And if you do the maths and think about it for a little bit, you'll find that it's the logarithm of this intensity, which is the radon transform. But of course, in applications, you have access to this intensity of X-rays. What you do not know is the density of the object. And so, you would want to invert the transform, and that's what Cormack did. And if you read his Nobel lecture, he'll be quite explicit and I think honest about the fact that he just was not aware of the work of radon.
In this case, do you need some compatibility condition for the function for the inverse transform to exist?
No, I don't. That'll come in a moment. The reason I do not is that the space of lines in this case is two-dimensional, so there is no restriction on the range of the transform. However, so we step back chronologically. The next contribution to this subject was made in 1938 by somebody called Fritz John, or he's German, so maybe Jon is the right pronunciation. So what he did is he looked at the radon problem, but instead of looking at R2, he looked at integrating along lines in R3. So now you have a function f on R3 subject to the same decay conditions or compactly supported conditions. Let me call this for, I'll try to number my formulae, okay? So this is section 0, and this formula here will therefore be 0.1. Okay. So you can still define this integral transform along all lines, but now the novelty of going to dimension 3 is that the space of lines has bigger dimension than R3. So the dimension of the space of oriented lines in R3 is 4. And again, in my concrete treatment, I'm just going to parameterize these lines. So parameterize the lines in R3. So maybe, sorry, instead of, I'll be changing my notation as I go along. Maybe instead of calling this x and y, I'm going to call this x1 and x2. And that way I can call this x1, x2, and x3. So now S goes to S alpha 1 S plus beta 1, alpha 2S plus beta 2. So I need 4 parameters for the line, and again I'm missing some lines. I'm missing the lines which are on which the x coordinate is constant. I'll be given that it's a mini course, I'll be offering some exercises. Sorry, how do you play the board? This goes up, so this can go up a bit. I'll be giving some exercises. One exercise is that if you do this properly, if you look at the space of all oriented lines in R3 without missing any lines, then it's still four-dimensional, but it's not as simple as, you know, alpha 1, alpha 2, beta 1, beta 2, but instead it proves to be a tangent bundle to a two-sphere. So proof, if you that the space of oriented lines in R3 is TS2. And you can then do what I'm going to do in a moment using this kind of more abstract geometry. But this will do for now. Okay, so what happens then? We're doing our integral. So now formula 0.1 becomes phi, which depends on alpha 1, alpha 2, beta 1, beta 2. It's an integral from minus infinity to infinity of f of s alpha 1s plus beta 1 alpha 2s plus beta 2 ds. However, if I give you a function which depends on alphas and betas, then this function will not necessarily arise from a transform of some f. So in this case, you do not expect the inversion formula to exist, and just because not every function is in the range of this transform. Okay? So generically, in fact, a function will not be in the range of the transform. Well, the question comes, how can you tell whether a function phi of alphas and betas can be written as this integral? And that was the problem which was posed and solved by John. So characterize the range, let me call this 0.2 of 0.2. Well, what can we do? We can start differentiating with respect to alphas and betas and doing this under the integral sign. So if I do d phi by d alpha 1, that's the same as this integral. Well, this coordinate is x1, this coordinate here is x2, and this is x3. Okay, so phi depends on alpha 1 only via x2, but I need to use the chain rule. So there'll be df by dx1 times s ds. If I do d2 phi by d alpha 1 d beta 2, then the beta 2 dependence sits here but without ds. So this is an integral of d2f dx1, sorry, it's not x1, it's, should correct me when I make mistakes, it's x2, and this is x2, and this is x3 times s ds. But you see, if I compute d2 phi by d alpha 2 d beta 1, if I first differentiate with respect to alpha 2, then I'll have df by dx3 times s. And then I need to differentiate with respect to x2. Okay, so if if this function is, if the second derivatives of this function therefore continuous, then these have to equal to this. So I discover that phi has to satisfy a differential equation on the space of all lines. It's called the ultra-hyperbolic wave equation, which is d2 phi by d alpha 1 d beta 2 minus d2 phi by d alpha 2 d beta 1 equals 0. Well, to bring it to a more familiar form, we could say, what could we say? We could say that alpha 1 is x plus y, and then we'd like to say that beta 2 is x minus y. It was renamed variables. And then alpha 2 will be t minus zeta, and beta 1 will be t plus zeta. And then the equation I have becomes d2 phi by dx squared minus d2 phi by dy squared, and then alpha 2 goes with beta 1, so I have minus d2 phi by dt squared plus d2 phi by d zeta squared equals 0. And this is a wave equation for a space-time which appears to have two space and two time directions. So there is a metric associated to this, which is dx squared minus dy squared plus d zeta squared minus dt squared. Okay? And the seminal result of Yon is that this equation characterizes the range completely. So if I give you a phi which satisfies this ultra-hyperbolic wave equation, then this phi will arise from some f. No, point 2. Okay, so, and this subject has then been evolving happily since 1930s, mostly in former Soviet Union. So the school of Gelfand and Gindikin made great contributions, and we'll leave this subject here and make a connection to what will be the subject of this course, which is Twistor theory. Now, but what we've learned so far, and as a spin-off from these considerations, is that if we want to solve in this ultra-hyperbolic wave equation, then all we have to do is take a function on R3, such that it decays away from, let's say, the origin, an arbitrary function otherwise, and integrate it, and we get the solution for free. Now, but this is not physics because the signature of this metric is wrong. Well, how would you make it right? Well, you would, for example, want to replace I by Iy, and if you do that, that becomes the wave equation on the Minkowski space. Well, you look back at your formula and say, what happens there? Well, if you replace I by Iy, then you have an I here, and you have a an I here. So alpha 1 and beta 2 become complex, and the integral is not real. It's not clear what you integrate over. It's not straightforward if you kind of, well, mathematically minded to see what's going on. But that is exactly what was done by Roger Penrose in 1960s. So Penrose was not aware of this line of research, John's formula, and he had his own reasons to look at contour integral formulae for Wave equations in Minkowski space. So the
was he aware of this Nobel Prize for the rediscovery of Rodin inverse?
well, that would involve a time machine, because this Roger's work is in 1960s, and the Nobel Prize. So 1965, which really is in the beginning of Twistor theory. So Penrose contour integral formula for a wave equation on Minkowski space. Okay, so I'm going to write down this formula out of the blue, but then we will see that this formula really is very close, well, it's an analytic continuation of 0.2. So phi of x, y, z, and t, now complex numbers will come in, so the integral I'll be working with will be a contour integral, and there'll be some contour gamma in CP1, this complex projective line. I should say that these things like complex projective line and complex projective spaces will play a big role in this mini course, so I'm going to, I'm writing it down here, but I'm going to introduce these things properly and define them in due course. And we are integrating f of, I think, t plus zeta plus I x plus iy, and then x minus iy, sorry, let me try to have this right. Not I, this will be some lambda, and then x minus iy plus lambda t minus zeta, and then lambda d lambda. Okay, so I'm taking an arbitrary function, although we might even divide it by 1 over 2 pi I. We're taking an arbitrary function of 3 complex variables. The first one, we can still call it, well, capital X1. The second one, and the third one. And lambda is complex number, so it can be also infinity, so it takes its values in the Riemann sphere. We're choosing a contour, and we're performing this line integral. Now, we don't expect any function, because we're integrating a function of 3 variables, and we're getting a function of 4 variables, and x, y, z, and zeta, maybe, let's call it zeta and t, are real here. We don't expect any function to result from this, but the calculation, as I've done here, so differentiating with respect to t, x, y, and z, and using the fact that the derivatives commute on f, will convince us, so we verify, that this function phi satisfies, and if I had my signs right, it'll satisfy exactly the wave equation on the Minkowski space. d2 phi by dt squared minus d2 phi by dx squared minus d2 phi by dy squared minus d2 phi by d zeta squared equals 0. And this we're going to call 0.3. Why did I do that? I mean, I've changed the order I do things on the blackboards. Right. So this, this is now known as the Twistor contour integral formula, or Penrose's formula, and it'll be our entry point to Twistor theory. So I'm going to ask several questions about this formula, and I tell you what the answers are, and then I'll spend the lectures elaborating on these answers. So the first question is, what does it, there is a formula, what does it mean geometrically? What is the significance of these three variables, x1, x2, x3, and f? So what is the geometric interpretation of 0.3? Okay. So, for example, where is this function f defined? The answer will be f is a function, and I say function in inverted commas because it's really not quite right, and I'll come back to this, but f is a function for now on a three-dimensional complex manifold. This manifold is called the projective Twistor space. And it's denoted PT to distinguish it from a non-projective Twistor space. And this projective Twistor space, as you'll see later in the course, is a complex projective free space with a complex projective line removed. Now what happens in the formula is you take this function on the complex projective free space and you're restricting it to a line parameterized by lambda, and then you're performing this integral. So this Twistor space, it'll turn out, admits a 4-parameter family of lines. And in the Twistor formulation of physics, certainly of special relativity, a space-time is a secondary object. It'll be this 4-dimensional family of lines. So in 0.3, f is restricted to a line parameterized by lambda. I should have said earlier that this function f is arbitrary, except the fact that it's actually holomorphic. So it's a holomorphic function of these three variables. Of course, you'll know that if you integrate a holomorphic function, if this function was holomorphic everywhere on CP1, then the contour gamma would not enclose any singularities, and by Cauchy's theorem, the answer would be 0. So it's holomorphic, but it's allowed to have poles. So f is holomorphic, except a finite number of poles enclosed by gamma. Okay, so we will elaborate on what this Twistor space is.
So is it
No, well, there are cases where you would allow for a central singularity, but it's meromorphic for now. Okay, so question 2. Question 2 is more for kind of mathematically minded people. You might ask, is this correspondence one-to-one? So, is it really the case that a meromorphic function f corresponds to a solution and a solution corresponds to this function? And the answer to that is certainly no, at least not as I've stated it. Why? Well, you can take f and you can modify it by adding a function to it which is holomorphic inside the contour. And if you do that, you're not going to change the integral. Another thing you could do is you could take this contour and you can deform it continuously in a way where it doesn't touch any singularities, and that will not change the integral either. Okay, and what's going on, it's quite subtle, and it took Roger Penrose 10 years to figure that out. I mean, the answer we know now is that you should not really think of f as a function, but as a representative of it's a first shift cohomology group, and so in kind of simplest possible terms, what you do is you look at equivalence class of functions f and contours gamma, and you're allowing to modify the function by something which is holomorphic in some open sets and move the contours. And if you do all that, then you can establish, prove a theorem. It was story was that when Roger moved to Oxford in mid-1970s, and he already had this formula, and at the time the geometry chair at Oxford was held by Michael Atiyah, who immediately understood this formula and what was going on, and he explained to Roger that that this cohomology is at stake, and in Michael Atiyah's own recollection, in about a few months' time, Roger Penrose's research group became experts in evaluating this cohomology. There are people, names Richard Ward and George Sparling, who were students in 1970s, who came up with down-to-earth ways of computing cohomology, splitting formulae, and what not. So just to continue on this answer, should think of equivalence classes as elements on a check cohomology. Okay, it's question 2. Question 3, and that's where I'll be taking this course, is, it's very nice that you can solve a wave equation using some fancy complex methods and geometry, but everybody knows how to solve wave equations. So does this formula 0.3 generalize to nonlinear equations in mathematical physics? Okay. And depending on who is kind of giving these talks, the answer you often hear is emphatically yes, but I'm going to say sadly no, it doesn't generalize, at least not to the equations you would really want it to generalize, because we are relativists, we'd like to solve Einstein's equations, and despite many years of research, nobody knows whether there is a correspondence like that for full Einstein's equations. But it is the case that there are constructions like 0.3 which provide in principle all solutions to a subclass of Einstein's equations they called self-dual Einstein equations, and the solutions to those are gravitational instantons, which I'll be telling you about. But the downside is that these gravitational instantons and these solutions which you can obtain do not exist in Lorentzian signature, and I'll explain why that is. So the answer, the honest answer, A3, is not to those you would really want to. Like Einstein. Can people still see if I'm that low? But yes, to others. What others? Well, I mentioned one class of self-dual Einstein responsible for instantons, as well as to all, or maybe almost all, equations we now call integrable. So you might have come across soliton equations like Sine-Gordon, Korteweg-de Vries, maybe some others, BPS monopoles, and they integrable. I mean, there is no universally agreed definition of what integrability means. People have different approaches, techniques, but it appears that all those equations people agree to call integrable have Twistor transforms like that. Okay, and let me ask last question, and that. Question 4. So this was question 3, answer 3, right? Yes. Question 4 is, does it generalize to higher dimensions? Okay. Because after all, what we're doing here is really fine-tuned to 4 space-time dimensions with the count on the dimension of the space of lines and points. And the answer to that is no. And for good reasons. I tell you what good reasons we'll have for that. And moreover, you should not be looking at those Anyway. Okay, so it's been, you know, this. So Twistor theory is, I mean, it's not a complete theory of physics. It's more of a program, you know, manifesto. But unlike other theories, you know, the fact that the space-time is four-dimensional is built in you know, formalism, and you know, there are very smart people out there, and they can generalize everything to every other context, and they've tried Twistors, and there are things you can do, but really Twistor theory loses its power. So you're, you know, what goes wrong, and again I'll tell you more about it when we have enough formalism for us to appreciate that, is that this balance between the dimension of a Twistor space and space-time is broken. So in the context I'll be discussing, the Twistor space is one less dimension than the dimension of the space-time, and that means that you can pick up arbitrary holomorphic unconstrained objects on this Twistor space and do things with them like integrate over a contour and obtain solutions to differential equations on space-times. And that's what you'd want to be doing, because the Cauchy surface, the space where you specify the initial data for Einstein's equations or wave equations, you know, it's codimension one, so it's one dimension less than space-time, and that should be equal with the dimension of the Twistor space. And in all these other generalizations of Twistor theory to higher dimension, that's broken, and it seems to me that the fact that it's broken means that you should not be doing it. Anyway, Adams explained to me that the deal is that I talk a bit and then I stop, and then I start talking a bit again. So I propose to stop now and we reconvene in a quarter of an hour.
Recording stopped.
Well, I propose to start at 3. No, 4, because this is Polish time. But this quadratic form doesn't have a signature. And then we'll recover various signatures by imposing reality conditions. So the coordinates on this complexified Minkowski space, I'll call them W, Z, W tilde, and Z tilde. And in terms of these coordinates, we'll have a metric, which is 2 dz tilde minus dw tilde. And we will have a volume form holomorphic volume form, which is dw wedge dz wedge dw tilde wedge dz tilde. So it's a Minkowski space with an orientation. Okay, and this doesn't have any signature because it's complex and holomorphic. So there are three possible ways of imposing reality conditions on this. And the first is the actual Lorentzian reality conditions. So there we'll set z to be t plus zeta, and z tilde to be t minus zeta, and they real. And we'll take w and w tilde to be complex, so w is x plus iy, and w tilde is minus w bar. And we're going to stick root 2's. Okay, and if we do that, then this metric G becomes dt squared minus d zeta squared minus dx squared minus dy squared. Okay. Another reality condition will be Euclidean. So Lorentzian I'll sometimes abbreviate as phat L, and that will be phat E. Well, here I take z tilde to be z bar, and sorry, let me just have I messed that up? I think I have, because I want my signature to be 3, 1. So if I'm doing, so this is dt squared minus dz squared, and now I have this minus sign here, so I need to put plus sign. I apologize. For this metric to be correct, w tilde has to be w bar and not minus w bar. Here, z tilde is z bar and w tilde is minus w bar. And then the metric becomes 2 dz squared plus dw squared, and that's positive definite. That has signature 4, 0. And finally, there is a possibility of keeping, and that was relevant in this John transform, of keeping z, z tilde, w, and w tilde all real. And in this case, the spacetime has signature 2, 2. Such spacetimes are called neutral or Kleinian or ultra-hyperbolic or whatnot. I call them neutral. And this is relevant to what we did in section 0 with John transform. Okay, so now there are there are 3 remarkable coincidences of isomorphism which happened only in dimension 4 and in no other dimensions. So I say 3 remarkable isomorphisms. So the first one is to do with Hodge duality. See, we have a metric and we have a volume form. We can define an endomorphism on the space of differential forms on any degree, called Hodge dual, so a star, and that maps P forms on M in our context to 4 minus P forms on M. And that is defined by saying, for example, that star omega wedge mu is G of omega and mu times the volume form. That's a coordinate invariant way to define this. And you see here, so omega is a P form, and this formula defines this endomorphism if it holds for all other P forms mu. So for all mu's which are P forms. Okay, so the left hand, so star of omega is a free form, you wedge it with a mu. Well, that's a 4 form, that's a multiple of the volume form, and we pin this down by saying that this multiple is an inner product of omega and mu. Now, what then happens is you look at this on the space of, you see what happens to this endomorphism on the space of 2 forms. So on lambda 2 of M, you find that in complexified Minkowski space, the way I've defined it, the star squared, so applying this hot star twice, gives you an identity. Okay, so what that means is, from a linear algebra perspective, you can look at the space of all 2 forms, and you can decompose it into 2 eigenspaces of this operator. There is an eigenspace with eigenvalue 1, an eigenspace with eigenvalue -1. And the way you do that, so this you have to check that this follows from my definition. You say, you'll say the following. You'll take, let's say that F, or maybe capital F, is a 2 form. We can then write F as a half F plus star F plus a half F minus star F. We could call this F plus, and we could call this F minus. And it's obvious that MEF can be written like that. Now, if we look at F plus and we apply star to this, then star applied to F is star F, and star square is 1. So we get F plus star F again. So this is F plus, and then star of F minus is minus F minus. Okay, so what this does is it gives you a decomposition of this space of 2 forms. So there are 6 2 forms in 4 dimensions, and we decompose them into 2 spaces, the space of self-dual and anti-self-dual 2 forms. This is called self-dual, this is called anti-self-dual. Call them gamma 2 plus M, gamma 2 minus M. And these are self-dual or SD forms, and these are anti-self-dual. ASD. Okay, and this is 6-dimensional, and these are 3-dimensional. We call this 1.1. Now, you see what happens with this decomposition and this algebraic property of a star if you start taking these real sections. Well, so what happens is suddenly not what you would want to happen, and which will kind of spoil, in some sense, Twistor theory in Lorentzian signature, but you'll find that under imposing these reality conditions, you find the following, that in Euclidean signature and in this neutral signature, the star squared is still identity on two forms. However, in Minkowski signature, star squared is minus identity. So what happens in Minkowski signature, your, the eigenvalues of star as an operator are plus and minus I. So you will have eigenvectors of these eigenvalues, and there will be two forms, but they will not be real. Okay? So in Minkowski signature, you do not have real self-dual or anti-self-dual two forms, but in these other signatures do. So no real SD or ASD two forms. Okay. Is this being recorded, by the way? So this is online. So know how many people can I offend in due course, but maybe not too many. Okay, so right. So what would be another exercise? I'll ask you to establish what would be the span of this, say, self-dual two forms using these coordinates I've introduced. Prove that the space lambda 2 plus is spanned by the following three two forms. There will be dw wedge dz, dw tilde wedge dz tilde, and dz wedge dz tilde minus dw wedge dw tilde. Okay, that's a basis of self-dual two forms. The first two here, this and that, they are simple. Like, it's d of a function, wedge d of a function, and they're, of course, null, so they have zero length, and the middle one is not. Good. So that's one. That's my first remarkable isomorphism. The second one has to do with spinors. Okay, so this is, this will come with a notation which people generally tend not to like, but it's kind of convenient to introduce. Do I really have to introduce it? It appears then I do. So, see, there exists two complex vector bundles. I'll talk about bundles systematically a bit later. If you don't know what that means, a vector bundle is an assignment, in this case, it's an assignment of a complex vector space of dimension 2. So I'm going to assign C2 to any point of my Minkowski space in a way which satisfies lots of axioms. But there are two complex vector bundles. Call them S and S prime, and they both equipped with symplectic structures, so they're symplectic vector bundles. epsilon and epsilon prime such that the tangent bundle to this complexified Minkowski space is a tensor product of these bundles. That'll be, you see, that'll be 1.2. And there is, a compatibility between the metric on Minkowski space and the symplectic forms. So, and if I take G of P 1 tensor Q1 with P2 tensor Q2, then that's the same as epsilon of P1 P2 times epsilon prime of Q1 Q2, and this holds for P1 and P2 as being complex vectors or sections of S, and Q1 and Q2 sections of S prime. Sometimes this formula is written more concretely using indices as GAB, where AB is kind of a vector index of Minkowski space, is epsilon AB, epsilon A prime B prime. Okay, and so here the indices A and B run from 1 to 4, and the capital letter indices, they label the sections of S and S prime. These sections are called spinors. So these are spinors, and these are spinors. They belong to different spin spaces. And A and B and capital letters, and also A prime and B prime, they either 0 or 1. And then this symplectic forms epsilon AB is 1 minus 1, 0, 0. Okay, so now using it, based on this isomorphism, it's convenient and it kind of gives some meaning into assembling these complex coordinates on Minkowski space into a matrix. So one sets XAA prime, so that's a 2 by 2 matrix, and that'll be Z tilde, Z, no, it must be, actually, yes, why not? W tilde W, and then G is the same as twice the determinant of dXA. Okay, so we'll think of coordinates as assembled into a matrix, and this assemble is based really on this endomorphism. Now, if I have a vector field, V, I can expand these vector fields into a coordinate basis using these coordinates. So I can write this vector field as V AA prime d by dx AA prime. You see, I can then compute the norm of this vector field with respect to the metric. And the norm of this vector field is, using this formulae, is just the determinant of the matrix of its components. So in particular, a vector field will be null with respect to the Minkowski metric if this determinant vanishes. So G of V and V equals 0 if, well, let's say determinant of VAA prime, which is the same in this spinor notation as epsilon AB, epsilon A prime, B prime, VAA prime, VB, B prime with a factor a half equals 0. Okay, so now referring to everybody's knowledge of linear algebra, if you have a 2 by 2 matrix and it has determinant 0, well, and this matrix is not identically 0, what happens to the rank of this matrix? Well, it has to be 1. Okay, the non-zero determinant 0 matrices have rank 1. So rank of this matrix VAA prime equals 1. And that means, and that's a kind of linear algebra fact, that this matrix can be written as a product of two, well, 1 by 2, 2 by 1 matrices. So VAA prime, we can write it as, well, so what is this VAA prime? Is V0, 0 prime, V0, 1 prime, V1, 0 prime, V1, 1 prime, and it's some P0, P1 times Q0 prime, Q1 prime, and one can write it using indices as PA, QA prime. So, okay, just to recap, go back to this isomorphism. It doesn't mean that every vector is a product of two spinors. This means that every vector is a combination of products of two spinors. But what we've just shown is that a vector is a product of two spinors if and only if it's null. So, in physics, if it's the trajectory of a photon, then you can write it like that. So null vectors decompose as products of spinors. Okay. There is also this is my second isomorphism out of remarkable 3, and there is a link between 1.2 and 1.1. So, and it'll be an exercise for you to prove that the space of self-dual two-form, so really the bundle of self-dual two-forms on M, is the same as a product of S prime dual symmetrized tensor product with itself. And you prove it by concrete calculation using indices. And there is a relation like that for anti-self-dual two-forms, right? So what that means is that, well, what you'll have to prove is that if you take any two-form, FAB, then you'll be able to write it as sum phi AB epsilon A prime B prime plus phi tilde AB epsilon AB. Correct. Thank you. Okay, that's the second remarkable isomorphism. So now the third. Okay. Yes.
So what's the relation between writing our matrix here and the sort of more usual trick where you write a vector as a matrix using the Pauli matrices, and then you decompose that into spinors?
Well, okay. So the thing about Pauli matrices is that there are 3 of them. So if you were to do these spinors in dimension not 4 but 3, then you would argue that the tangent bundle to a three-dimensional Minkowski space or Euclidean space is a tensor product of a spin bundle with itself. You would only have one type of spinors, and they would be in terms of Pauli matrices. But these are four-dimensional spinors. I'm going to maybe allude to a more concrete answer when I discuss my third isomorphism. And I need to decide where I do it. So how did I call this? Hodge duality, then I called spinors. And the third one is the orthogonal group. Okay, so it's a unique property of rotations in dimension 4, real or complex, that the relevant orthogonal group, which is SO4C, why SO4C? Because we have a metric in 4 dimensions, and we're consider orthogonal transformations preserving this metric. This is not simple, but decomposes. I want to give it a number. It decomposes as 2 copies of SL2C. So SL2C times SL2C, let's say tilde, over Z2. And this will have a number, God knows what number will it have. Can you, anyone who takes notes, what number is that? 1.4 maybe?
Probably 1.3.
1.3, because it's a third. Good, thank you. Okay. So now, okay, so these SL2C groups, they, each of them acts on its corresponding spin bundle. So the relation of 1.3 and 1.2 is that S and S prime are representation spaces of one SL2 and the other one. Now, in the complexified setting, these SL2 groups are very independent. But again, the reality conditions, depending on what conditions we assume, make some further reductions. And the condition you will become familiar with, especially those of you who come from the Warsaw School, is the Minkowski reality condition, where these are not independent, but they're related by complex conjugations. So in the Lorentzian 1-3 signature, SL2C tilde is really SL2C bar, and you realize this endomorphism by saying that instead of transforming a vector by a Lorentz transformation, I'm going to transform the corresponding matrix, this matrix VAA prime, by a product of 2 SL2 transformations. So VAA prime goes to some VB prime, maybe MAB and MA prime B prime, and this one has a bar on it, and this becomes this is an element of SL2. And this is an element of its conjugation, a conjugate element of SL2. Okay, so and it's actually easier to implement this often easier than Lorentz transformations. What happens in the other 2 signatures is different. So in Euclidean signature, the relevant group is SO4R, and that's locally a product of SU2 and SU2 tilde. Okay. And in this 2,2 signature, the relevant orthogonal group is SO22, and that's a product of SL2R and SL2R tilde. You see, and it's only this signature which has an invariant complex what it means for a spinel to be real. So if, we take, well, so if P is a section of S, then the SL, well, one of these actions on P is PA goes to M B A P A. So only in this 2,2 signature and a condition P bar equals P is invariant. Okay, so very concretely I'm saying that PA, it has two components, P0 and P1, and PA bar also has two components, P0 bar and P1 bar. See what happens in Lorentzian signature, a complex conjugation takes you from one spin space to another. They related by a conjugation. In Euclidean signature, the complex conjugation like that is not preserved by SU2 because SU2 is complex itself, but in this Kleinian signature, it is. Okay, so the three different real sections of 1.3. Let's go back to Lorentzian signature and see kind of one appearance of complex numbers there. So in Lorentzian case we have therefore SO31 is locally up to this Z2 isomorphic to SL2C. Okay, and this might be a right place to mention Penrose's complex numbers in the sky. Okay, so what's that? Well, you see, it also goes under the name of a celestial sphere. So here you take an observer and the observer looks at the night sky and sees a sphere full of stars. So what they really see is an intersection of their past light cone with some Cauchy surface, some surface t equals constant, right? So these stars really existed in the past of this observer, but the light reaches them after some time. So this S2 is an intersection of a past call the observer O, past light cone of O with T equals const surface. Okay, so a light cone is a null three-dimensional hypersurface, but its spatial section is two-dimensional and it's a sphere. Now, imagine that you have not one but two observers, and these observers have some word lines. So that's a word line of observer O, and that's a word line of observer O prime. And they meet somewhere, and O has their celestial sphere, and O prime has their celestial sphere, and they want to compare them. So how do celestial of O and O prime compare? So you see, to answer that, we have to, we can think of these spheres not as two-dimensional real manifolds, but as one-dimensional complex manifolds. So if we take a sphere in R3, let's say that U1, U2, and U3 are the coordinates in this R3, and the sphere is given by U1 squared plus U2 squared plus U3 squared equals 1. Then we can stereographically project this sphere onto a plane from either the North Pole or from the South Pole. Let's do it from the North Pole first. You see, and then you find, and so you project it onto a plane, and then you identify this plane with a complex plane. So what is the complex coordinate on this plane? Well, you can work it out to be lambda, which is U1 plus I U2 divided by 1 minus U3. But you see, by doing that, you have missed one point. You have missed the point where U1 and U2 are both 0 and U3 is 1. So you've missed precisely the North Pole you're projecting from. So instead, so this is projection from N, you could project from S. And that gives you some other coordinate, lambda tilde, and that one is U1 minus I U2 divided by 1 minus U3. Now you're missing, divided by 1 plus U3, I'm sorry. Now you're missing the South Pole, which is 0, 0, minus 1. Now you find that on the intersection, so you know, the north, you project from here, you've missed one point, you have an open set, which is the sphere minus this point. Here you have another open set. So on the overlap, calculation will show you that lambda tilde equals 1 over lambda. So that's like, you know, in manifold theory, you define a manifold by a transition function or a set of transition functions if there is more than one open set. So we've done this here with a sphere. We have lambda and lambda tilde as independent coordinates, complex coordinates, but this transition relation between the two is a holomorphic one. It doesn't involve lambda bar. And that's what the fact that it's holomorphic, that means that we've equipped the sphere with a structure of a complex manifold. So this is a transition function for a one-dimensional complex manifold, and this one usually is called the Riemann sphere. Okay, so we have so this step was just to remind you or tell you how you turn a celestial sphere into a complex manifold. Now you see, Roger Penrose's view has always been that if you want to think of any unification of quantum mechanics and classical physics, then the mathematical formalism should reflect that. Now, quantum mechanics, as we understand it, is based on complex numbers. So, you have Hilbert space and wave functions, but they really have to be complex to superpose them to explain double-slit experiments. It's inherently complex. Whereas special relativity and general relativity is at its core real. I mean, you can introduce complex numbers as tricks, but it's a real manifold, real theory. So one goal of this program is to bring complex numbers at a fairly fundamental level. And this is a kind of first little attempt at that. You see what the calculation will now show you, but having identified this S2 with a Riemann sphere, we have lambda. We can now go back to this question: how do celestial spheres of O and O prime compare? So if O and O prime are related by a Lorentz transformation, and this Lorentz transformation is represented as an SL2C matrix, alpha, beta, gamma, delta in SL2C, then you'll find that this transformation between the following celestial spheres is what's called a Mobius transformation. So it's alpha plus beta lambda divided by gamma plus delta lambda. Okay, so simple transformation for celestial spheres. Okay, so I'm out of time, so that's where I propose to stop. And the lectures I'll be writing tonight and delivered tomorrow, I wrote a note to myself. I'll tell you about complex projectives. So now we'll be moving to Twistor. I've got these three remarkable formalisms. We'll now move to Twistor theory. I'll be talking about complex projective spaces and define the Twistor space and incidence relations. And we'll see how far we get.